Bismillahirrahmanirrahim. I'm to start with the lecture on the topic which we covered in our last lecture. I'm going into a bit more detail with some rational example to make it more comprehensible for you guys. I'm going to discuss again one-part synthesis. Why we are to discuss this topic, as I already told you, one-part synthesis come under the term which is broadly the eco-friendly reactions, greener reactions. That's why we are studying it. I'm trying to make you understand about the topic as a part of your syllabus, as a part of your course at the semester number 4 in your BS exam, BS course. This seems to be a bit difficult to comprehend, but I'm trying to make it graspable by coming to your own level, by taking simple example of benzene reduction, oxidation, this sort of reaction I've explained to you last time. Today I will take a bit rational example, which is a bit very much known in literature. Let's say very known reactions are there. If you start off with this sort of compound benzyl bromide and we reacted it with sodium azide NaN3, it's a negative, it's a positive. It shows a nucleophilic substitution reaction. The reaction is usually done in DMF, dimethyl formamide, as a solvent. The reaction could take 3 to 4 hours. Then what happens? As a result, this bromo is substituted with azide. We get this product which is called benzyl azide. Then let me explain it a bit more for you guys. We take a flask, we put in DMF in the start, dimethyl formamide, it's a solvent. We take like 4 to 5 mLs. If we are going to run the reaction on 1 to 2 millimole scale, the scale is a bit lower for the organic synthesis. At the start, actually, we perform reactions on a lower scale. 2-3 millimole, we need to have 4 to 5 mL of DMF in the flask, reaction flask. We put in, let's say, benzyl bromide first. The flask is on a sort of a stirrer that is stirring it. Then we put in sodium azide in 2 to 3 portions. Then we let the reaction to run on stirrer for 3 to 4 hours. We keep checking the reaction using simple TLCs. When the reaction completes, the nucleophilic substitution, we get this sort of the product. Now the flask contains this product. This product is present in the flask. Yes, the remaining sodium in the form of sodium bromide will be there. We will have a DMF as well, which is a 4 to 5 ml of the solvent. So it's a product, but we have 2 extra things as well. So what we use, we take this reaction mixture, we call it reaction mixture, and we we pour this reaction mixture into a separatory funnel. You guys have an idea about the separatory funnel. We put this reaction mixture into the separatory funnel. Then into the separatory funnel, we put in certain organic solvent which can dissolve this product. Because it's an organic reaction, our product is an organic entity, it could be dissolved by certain organic solvent. Let's say we can put diethyl ether, or we can use dichloromethane like 5 ml. Then we add a bit of, let's say, 3 to 5 ml of brine. Brine means water in which we have mixed a little bit of sodium chloride to make it a bit polar, because we need to remove this DMF out. We want to remove DMF out along with the water. Then this product will be dissolved in dichloromethane, or if we are using diethyl ether, this will go into it and the salt will go into the water. We will separate the two layers and then we will evaporate the solvent, whatever was being used, and we will receive the product. So at the first step, the reaction completes in 3 to 4 hours. At the end of the reaction, we need to remove DMF as well as sodium chloride using water, and then dichloromethane or diethyl ether, whatever the solvent is available with us. We need to use this 5 ml at least 3 times. We put one time, we extract it, maybe little bit of the organic compound is still in the water. So we extract first organic layer, put it separate, then we take 5 ml of the organic solvent again, we put that again into the separate funnel, shake it well, and then we separate it out, then 3 times again. So it means we are going to use at least 15 ml of dichloromethane, which at the end will be evaporated into the environment to get the product. So we have used two sort of solvents. Number one, the solvents as a DMF, where we have run the reaction. Number two, the reaction of solvent of the dichloromethane, which has been used as our extraction medium. So 15 ml plus 5 ml, almost 20 ml of the solvent has been used. At the end of the reaction, there's 20 ml of the organic solvent is going to enter into the environment. So we will receive this product. When we have received the product, we will take again another flask. Let's say we could use DMF again. We have put the DMF again. This process is called extraction. Ultimately, it is called purification, because we have purified the product. Now this purified product, which is benzyl azide, we have taken it into another flask. So we put benzyl azide into it, this one. Then we are going to add another our reactant. This is called phenylacetylene. It's a triple bond, phenylacetylene. We are using, as I've told you, the same solvent, same sort of, not same mean that DMF has been discarded into the environment now. Now we need to have 4 to 5 ml again. New DMF has been taken into the flask, and we will put sodium azide into it. Let it stir for a while. It's a number one. Then number two, we will put in the reactant number 2, which is the phenylacetylene. Then after one, we will put in the catalyst. It's a catalyst. It's a catalyst, and the catalyst is copper sulfate along with sodium ascorbate. Why we use that, it's altogether a different story. So we use them together. So what comes out of this reaction? This reaction takes like 12 to 18 hours depending upon different solvents. At the moment the solvent is DMF, we can assume that the reaction completed in 12 to 14 hours. What will be the product then? This is going to be the product. This carbon along with 3 ends. This carbon along with 1, 2, 3 ends, and this phenyl is on this side. So your reactant number 1 is on this side. Then you have a carbon number 1, carbon number 2, this is carbon number 1, carbon number 2, and this is the phenyl ring over here, it's on here. This double bond has been converted, triple bond has been converted into 1 because one of the triple bond which was present over here, it moved from here to here, from here to here to make a bond with these two buddies. So you will have this sort of a product. This is called some sort of a triazole. This is the product. So let me explain it in a real fashion again. So we have a flask, flask number 2. We took DMF as a solvent, and then we put in, as I've told you in the beginning, we put in azide first, then we put in an acetylene, then we put in catalyst which is copper sulfate along with sodium ascorbate. It's a catalytic system. After 12 to 14 hours, these two have been consumed, supposed to be consumed. The catalyst must be over there and the product would also be there. So there is a product inside the flask after 12 to 14 hours. So these bodies are supposed to be disappeared now, or maybe little bit fractions, only few molecules may be present, but mostly they're supposed to be disappeared because they have reacted to produce this body. So this product is present inside this one. Again, we have a DMF present in the flask, and the sodium part of an ascorbate, sodium sulfate. You have an idea, it's a sodium sulfate, it's an inorganic salt. So we were using DMF, dimethyl formamide, as an organic solvent. So it would also be there, it won't have gone anywhere else. So the catalyst is in the flask, the solvent is in the flask, the product in the flask. So again we need to purify that in order to get only this one. Again we will take another separatory funnel, take this reaction mixture, pour into the separatory funnel. Okay, then again we have all three things in the separatory funnel. In order to extract the product, we need to have dichloromethane again. 5 ml 3 times, 1 time, 2 times, 3 times. Every time it will bring out the product along with the solvent. Two layers will be separated. One will be the water layer, the brine layer, which will carry these two body out. So it can be discarded. Water along with copper sulfate and this one. And dimethyl formamide, being a bit polar, can also be into brine. And then this product is supposed to be in the dichloromethane. So we need to use dichloromethane again 3 times at least. So 3 times means 15 ml, 4 to 5 ml, 20 ml again. So as a whole, this product has been formed in 2 steps. Step number 1, where azide was generated. In step number 2, this azide was used along with phenylacetylene to give this product. So this product from here to here is achieved in step number 1. Step number 2, dimethyl formamide was used twice, extraction one was done twice, brine was used twice for the extraction. So we suppose that the reaction proceeded well in 2 steps. The product is supposed to be a bit more purer due to the involvement of purification at each and every step. But on the other hand, the DMF, it's an organic, dichloromethane an organic. When it is supposed to be released into the environment, it is going to pose serious threat to our environment. So people came up with another idea. They said we can do this reaction in a single step using one pot strategy. We will not be using two flasks. We will not be using DMF 2 times. We will not use dichloromethane 2 times. We will not be using extraction 2 times. So they reduced the reaction to a single step. What they did, they started off as usual. They took benzyl bromide, they put in sodium azide using DMF, yes, 4 to 5 ml, let the reaction run. It is displayed as a nucleophilic substitution reaction. So benzyl bromide was formed. They did not purify at this step. They did not purify it. This was present in the flask. They put in benzyl bromide. Can you see that or no? It's going to be a bit higher. So they took one flask, put in benzyl bromide into it, have DMF in it, and then they added sodium azide, let the reaction run. As a result of the reaction, this product would have been formed in 3 to 4 hours. It will be sodium azide, benzyl azide like this way, like this one. So without purifying at this step, they simply moved on. As the reaction completes, they put in the next reactant without purification, without removing sodium bromide, without purifying this azide product. They just put in the next reactant, the next, which is involved in the next step. So what happened then? They put in this one into it. As a result of the reaction, yes, they put in this one, then at the same time they put in copper sulfate, they put in sodium ascorbate, but at this time they did not put in DMF. No need of this one because the flask is the same, DMF is already in. So 5 ml of DMF has been saved. The same, they will react in the same reaction flask, so they will produce the same sort of the product. I will write it as a product. It is in the flask. It will be produced, yes, next 12 to 18 hours. The same reaction time will be taken by the next step. So product will be formed. How you imagine that the product has been formed? As I told you, you can simply check it by using PLC thin layer chromatography. What's that technique? It can be discussed in any other next lecture, you know. So this product is there. Now the product is here in this flask, the final product. So then again we can take this reaction mixture which carries this product in it. We can pour into the flask, and then again we can bring in diethyl ether or sodium or dichloromethane, whatever is available in our lab. We can use that one as an extraction medium. Yes, again we will have to use it 3 times at least, along with brine, water, because we want to remove inorganics from the reaction mixture. So copper sulfate will be soluble in water, so we need to use brine. Brine means the water which carries a little saturated solution of water with sodium chloride. So in a way we will remove the contaminants, we will remove DMF, and we will remove, we will get the product in the dichloromethane extraction. Then we will evaporate dichloromethane at the end to receive the product. Now the reaction which was supposed to proceed in 2 steps has been completed in a single flask in a single step. In doing so, the dichloromethane's usage has been reduced to 50%. It has been reduced 50%. We are using only around 15 ml along with 5 ml of this, maybe 20 ml. So 20 ml on two steps has been reduced to 20 ml only. So in doing so, you have saved the organic solvent, which can be a costly. Yes, you have made this reaction an economical by saving the organic solvent. Secondly, by saving the amount of dichloromethane which was being discarded into the environment, we have made this reaction as an eco-friendly or a greener reaction due to one pot strategy, where one flask has been used, one solvent has been used for the preparation of the product. A two-step reaction has been converted into single step, which requires only I would say, which requires only one-time extraction and one-time addition of organic solvent for as a reaction media as well as for the extraction media. So we have saved it. So this is how I'm trying to convey you guys about the importance of the one-pot reactions. The importance in a way that they are green reactions, they are eco-friendly reactions. Last time we discussed few examples, like I started off with nitration of benzene, then I moved on to the reduction of benzene generating an aniline, then I would have thought of some other reactions similarly, but maybe the first reaction step, that was the nitration, it requires acids. The second reduction may be an idea that certain reducing agents are acid sensitive. So first reaction, that's okay, possible, but the next step may be sensitive to the presence of minor amounts of acids, remnants of the first step. So it can be problematic. That is why all reactions, they can't be the one pot. Out of 100 reactions only, there are few chances of 1 to 2% of the reactions that they can be converted into one pot reactions, where there are chances that the first step and the second step could be done using the same sort of solvents. That is very much the requirement. Secondly, the product of the first step should be a reactant of the second step, so it can react in the second step to give you the product. If this product of the first step is sort of an insensitive, it goes to decomposition, it's unstable, or it does not react the way you want to react it, then such reactions are not possible. So that's why there are a number of limitations there for the one pot strategies. From the last lecture and then from the follow-up questions from my students, they were thinking that each and every reactions can be converted into one pot. So there are limitations. Yes, it's really demand of the present era that all reactions should be eco-friendly, they should be greener, they should be non-poisonous for the environment. But it's not that simple, my young lads. It's not that simple, because one step is the requirement of the one step could not be the requirement of the step number 2, and then the requirement of the step number 3 could be different from the 1 from the 2. So that's why all reactions, all steps have different requirements. They can't be. There was a question from certain student how that is economical. So I think you have got the idea how such reactions are economical. Then someone said the contamination from the first step can be avoided by washing the flask before we are going to start the next step? Somebody asked the question. Yes, students are there to ask any sort of questions. My dears, as I've told you again here, once your first step is completed, you check the completion by TLC only, or there are other modern techniques in there, but in a simple lab, if you have a simple access to TLC only, you can see whether your reaction has been completed or not. If that reaction the first step, the reaction has been completed, you can put on the next reactant and let them react for the next number of hours till you receive the final product. Again, the formation of the final product will be detected again, will be confirmed again by the TLC. So from here to here, then you put on the next one. You don't have the time to wash the flask. You can't wash, okay, because we are not taking the first product out. We'll keep first product in, then you will put this next reactant in the same flask, and then let them move on. Let them react again for the formation of the final product. So 2-3 questions were there which came into my mind now, and I've explained how the reactions are economical. Yes, you got the better idea of their economical. Secondly, the contaminants cannot be avoided because you can't wash the flask at each and every steps. Some of the contaminants of the first step can move into the next step, but such reactions are put together to make them into one step, which are not that sensitive to contaminants. Yes, there are more reactants, there are more intermediates, they are sensitive to the contaminants, then they cannot be put into one pot strategy, one pot reaction. That's why one pot reactions are not that much known. They're only 1 to 2% only out of the 100% millions of known reactions, because of the limitations of the sensitivity and the requirement of each and every step. So this was the rule, this was the strategy demonstrated by one of the scientists, where they put one step and the two step together into this and done the reaction in single step. However, first reactant was reacted first, the product, when the product was formed, then they put in the next reactant to receive the product. Then if you imagine, the first step takes 4 to 5, 3 to 4 hours, and then 12 to 18 hours. The total time could be 20 to 24, 22, 24 hours. You have an idea, for running of the reactions we need stirring. We put the reaction on stirring, we let them stir. The stirring requires the electrical energy, the supply of electricity for constantly for 12 hours, 20 hours, whatever the reaction time. So means you are consuming energy, you are consuming electricity, especially in it can be a problematic in a country like Pakistan, where we are feeling always electricity shortfall. So somebody look into this one. That's the reaction completes in 20 to 24 hours. Requires too much energy. So it is a greener, it is an economical in one way that it has saved the solvents, but still the energy is being consumed. So they come up with another idea that was more fascinating. The more fascinating idea about the one pot reactions, I can explain it. So what the people do, actually did, but the next gentleman came in, they said, okay, no issues, put bromo, benzyl bromide, put in sodium azide, and then they said, put phenyl acetylene at the same time. 3 of the reactants were put in the flask at the same time. Means Someone took a flask. Yes, 5 ml of the DMF was taken into it. They put in benzyl bromide. They put in sodium azide reactor number 2. Then they put in reactor number 3. Okay. Then they put in copper sulfate and then sodium ascorbate. It's a catalyst system. Both of make the catalyst system. They put in together. What happens then? They all are present in the flask. It reacted it with this one. Yes, it produces benzyl azide. As soon as azide was formed, this goes to react it to give you the product. So as soon as the next molecule react to produce this one, the next comes here to give the product. So all were happening at the same time. Nucleophilic substitution reaction to give benzyl azide, then cycloaddition reaction of the azide with the phenylacetylene to give you the product. All was happening in the same flask. The reaction took 12 to 16 hours only. Means the gentleman reduced the time from 24 hours to, let's say, 15 or 16 hours. He saved 8 hours. Saving of 8 hours means saving of electrical energy that was being supplied to the reaction for its stirring purposes. So now the reaction has become more greener, more eco-friendly due to two reasons at least. Yes, only DMF was used once only. Secondly, the extraction was done once only, as the product will be formed after 16 hours. Thirdly, the reaction completes in less time, 16 hours. That's the biggest achievement again. The consumption of energy has been saved, has been reduced to at least 40, 30, 35, 40%. That's a big percentage if you consider this reaction on in an industrial aspect. We were discussing to run the reaction on 1 or 2 millimole scale. In industry, such reactions are run on, let's say, 100 moles, 100 kilos. So if that much amount is going to be used, the dichloromethane, your DMF is going to be used in many liters. Similarly, you need DCM, dichloromethane, for extraction in hundreds liters. At the same time, when you have a big flask, big containers to run such reactions, you need big stirring, huge stirrer, which could consume huge amount of energy. So such saving of energy does matter a lot for industrial point of view. So this is again one pot, 2-3 components, 2-3 reactions have been put together into the same flask. Such reactions are called multi-component one-pot reactions or one-pot synthesis. Multi-component, many components have been put together. 1, 2, 3, 4 components, 1, 2, 3 at least, have been put together in the same flask and let them run together. It's a multi-component. Okay, so this is also the one pot. The initial was also one pot where 2 were reacted first, and you waited for the formation of benzyl azide. Then you put in the phenylacetylene in the same flask, but the reaction took 24 hours. In this case, the reaction time was reduced. Why reduced? Because in the beginning we waited for the reaction of these two bodies. Substitution happened 100% in 4 hours. Then it was able to react with this one in next 12 to 18 hours. In this case, what's happening? When they react together, even a single molecule is formed, it reacts with this one. Again, we are not waiting for the 100% conversion. one reaction come over, it goes to react over there to give the product. Next molecule reacts to produce this one, then next molecule comes over there to give the product. So everything happening at the high pace. So reaction time reduces. So this is how we call it multi-component, one-pot multi-component reactions, and they are eco-friendly, economical reactions. How they are eco-friendly and economical, it has been shown to you guys. I've tried to give you a bit very simpler example so that you can understand what the molecules are, how they react in one step, in two steps, how they are called one pot reactions. When the same reaction becomes multi-component one pot reaction, I think you got the better idea now. So there are so many reactions in this category which can be discussed, but at the moment organic chemistry or the synthesis is not your main area. Your subject is a selected topics in chemistry where we are going through different topics, and in this category you have one topic that is called eco-friendly reactions. In order to make you understand what are eco-friendly reactions, I have to discuss one pot reactions, and into the one pot I have to describe the multi-component reactions, and I'm trying to give you an idea how they are greener, how they are eco-friendly. Reduction of steps, two-step reaction has been reduced into one step, so automatically it has become greener. Reduction of step means usage of solvents has been reduced to 50%, as I've shown to you guys. The same way, another approach where the time of reaction has been reduced. Time of the reaction ultimately means the saving of the electric power that is given to the reaction in the form of stirring. The reaction has to run with stirring, and stirring requires electrical energy. So the one pot reaction saves those supplies of energies as well. So they become eco-friendly and green reactions, and economical as well. So few of the questions which was raised from the students, I'm trying to cover into this. In addition to this, there are many types of I would say there are many types of one-pot reactions. Very complex examples are there: sense of drug molecules, sense of polymers, sense of coordination, complexes. There are many examples, but I'm not going into those because I've already told you it's a simple subject where just my requirement is to give you an idea about the eco-friendly reactions, green reactions. That's I've discussed only this one. If you have any questions related to the today's lecture about these examples, you may come up. You can WhatsApp your questions. You can put those as in comment area, or you may contact me through email. So I will be happy to answer those. Really, the main reaction which has been discussed in this today's example, that is called cycloaddition. Maybe it is new for you, or it has happened. As I told you, there are carbons. It's a benzyl azide. We try to keep this bond, try to move this way, and this bond try to move this way, this moves this way. So we have a sort of a cyclic structure over here. We generate a 5-membered cyclic structure here that gives you a triazolic ring. That ring is called a triazole, a five-membered ring, having three nitrogen atoms. 1, 2, 3 is called a triazole. It's apart from the benzene, phenyl CH2, and then 1, 2, 3 over here. It's a phenylacetylene, carbon, and then it's not your subject area. I think we haven't discussed yet cycloadditions in you as a part of your main subject, but I've discussed over here as a part of the eco-friendly reactions. We will get a chance to go through the cycloadditions, what they are, what are their reactions. I will give a separate lecture on cycloadditions as well. You will find these reactions interesting as well. They're a bit a sort of a less known to you guys, very much known to the world, but less known to you guys at your undergraduate level. So this is how I'm finishing today's topic. That was on one-pot reactions. I've given you only a single example, and try to convince with my idea, explaining it in two different ways. So I think you would have enjoyed it. It will have given you a bit more knowledge about the reactions, about the type of the reactions, economicals and greener. So thank you very much. I will be waiting for your comments. Thank you very much.